this work. This approach is very sensitive, but what is bad with this, when you do something sensitive, you may think about how it is sensitive not to the useful information, but also for the information that is interfering. There was another approach to see the special autocorrelation in the frame. You look at the autocorrelation and you see some peaks, you see some, but the information is in the wings. The frequency, the special frequency in the wings that gives you the thickness of the film, and with this information you can judge how fast the tear film is thinning, becoming more thin. Another approach is to look for the refraction. I'm not very a fan of this approach when you see the several components, Ziernicke components, and looking how the Ziernicke components are fluctuating. It's, to the diagnostics, to my mind, it's not a very, how to say, fruitful. But refraction, the total refraction of the eye, also contains some information about the tear film. The authors here, what they did, they grouped the Ziernickes, for example, S6 and S4. It's like a spherical-like aberrations, and also the same with the coma aberrations and the total. And you see probably, if you follow in the time, you see how the wavefront map is changing, the dynamics. And look, the Landau's also changing. You see how the focus is changing. So spherical is influences on the focus as well as coma. And you see that in some moments, for example, at 4, you see the Landau's more sharp than later. So the conclusion, the information is available in the refraction map. So let us look at that. And these authors decided to compare what's happening on the cornea and what's happening on the retina. And they made the instrument simultaneously looking on the shape of the tear film directly on the cornea and on the retina. And you see some changes in placidos, and very good seeing the Scheck-Hartmann picture. It looks very natural, like you see the distortions. This is another approach. It's called residual wavefront. If you work with the wavefront, you know that to get the wavefront, you do some approximation. Either approximation or interpolation, but normally it is approximation with the Ziernicke's polynomials or Fourier polynomials, or for example, Skander, like some more complicated polynomials. It doesn't matter. But if you get the polynomials in each point of your measurement, you have the measured value and the value which is approximation. And between these values there's some difference, which the author call residual wavefront, residual wavefront error, residual. So this difference between measured and approximated. And they made the experiment following the frames, like usual frames after blink. 1, 2, 3, 4, and they see that it plays. This residual wavefront is changing, varying. Come on. Should I push the buttons? No. Maybe here. Where did the left or right? Yeah. Here is the ray tracing instrument. This one of the screens of this instrument is like here. To the left are the points of hitting the eye, and the left bottom is the retinal spot diagram. So the diagram that shows where the laser beam hits the retina. In the middle, there, David asked me about XY, so that is X detector and Y detector. So they give a cross-section of the point spread function. It's a point spread function in each point. You get a point spread function in each point. And if you see, you may look, red is the number of the element of the multi-element detector. Detector is 512 elements, and this is the number of the element, red. And blue is the level of the signal. So you may follow either the coordinate or the level of the signal. So in the sequence of the signals, you will see that they change in the coordinates. Look, red readings are changing. Red line, it's the maximum. It's, I would say, changing, varying. So, to get the information, you can measure the change of coordinates, or you change the width of the signal, the width of the point spread function in each point. So, having two sources of information, position and width of the point spread function. Refraction changes the position, but scatter changes the width of the point spread function. So you have a rich information from the refraction measurement, more than when you follow the procedures. That is changing the coordinates, and that is changing of the width. So what we do, you see here 6 rings of points to the left, and to the right there are the projection of these points on the retina. A reference is blue, or maybe vice versa, it doesn't matter, and red is the next frame. So in each frame, you may compare the position of the reference and of the current frame. And from this information, you will build, reconstruct, you can follow the tear film up to the breakup. But there is one problem, not big, but still the problem, because the eye accommodates and makes a saccades. So it moves all the time, and changes the power. And here is the example how the left drawing shows how the saccades changes the position, and the right shows how the accommodation is changing the point spread function, the retina spot diagram, sorry. But no problem for mathematics. You make the transformation of the coordinates, so you move the total picture, for example, with the, in case of saccades, and you change the scale. It's very simple operation for mathematics, and as a result, you get the diagrams how your refraction is changing in time. These two examples. This example is one of our employees, and this is suggested from clinic, suggested the dry eye. What is interesting, that in placidos, you have a blind zone in the center. With the retina, you do not have it blind. So if you combine them both, you will have the whole field covered with data from wavefront or the data from the placido. That is all. So maybe this topic will be interesting for you. By the way, Tracy would be happy to have a contract with the university to continue his studies. So if somebody has the interest, we shall have a contract and work on that. Come on.
Thank you very much, and now we open for questions. Yes. Okay.
Vasyl, thank you for interesting presentation. But what do you mean to cover in the meaning of the wavefront? The last slide. The last slide of your presentation, you said that you can cover the placido discs and the retina without this hole. And yeah, and actually simultaneously, but from another hand, in which value do you want to cover? As a wavefront reconstruction, or?
I asked our medical employee to do it at least to do it separately. We can do it now. For now, we can do it simultaneously.
Okay.
So we make it and have the sequence of placido and the sequence of refraction.
And
so
covered.
In the future,
Okay. Sure. Okay, thank you.
Okay, thank you.
I have a question about the changes of the pupil size, because here I'm speaking. Okay, so because the pupil size changes immediately after the blink, is it also taken into account in the analysis? The pupil changes and size.
So do you take into account the change of the pupil size during the analysis?
I showed you how we follow with changes in second. And we didn't measure, in our experiment, we didn't measure the size of the pupil. If it changes something, we shall see it on the refraction. And to my mind, it's a solvable problem because you will apply the same thin transformation for that. Either changing the scale, either changing the coordinates, it's all calculatable.
So,
I don't see the big problem. At least not solvable problem. In my mind, it could be solved.
So, Vasyl, I'd like to follow up on that question. So, if you look at the sampling points across the pupil,
Yeah.
they're very simple.
Yeah.
Okay. And if I had a 10 millimeter pupil, are you saying that you're expanding the Zernike's? That's very dangerous. You can downsize to smaller pupils, but going up without any sampling information, you really don't have information about the
Why is it
wavelength.
dangerous?
I'm sorry?
You said it is dangerous. Why is it dangerous?
It's
the wrong answer.
Yeah, you hit the wrong. Yeah, you have no data to check to see if you're getting the right answer.
We didn't spoil any eyes.
Yeah. Well,
We experimented on our eyes. Only the placebos were taken from the clinic. So clinic was placebo.
yeah.
All other thing was with the people whom you know, with their eyes. But it works.
Okay, let's thank the speaker again, and let's welcome Pien.
Good afternoon, everybody. My name is Pien Vinke. I'm from the University of Murcia, PhD student, and I'm going to tell you a bit about my research about the assessment of the anterior film quality based on the dual visible and thermal imaging instruments. So in the previous presentations, it's already a bit explained what is dry eye disease, so I will make it shorter here. So the disease is a prevalent condition that significantly impacts the ocular health of millions globally. The dry eye disease occurs when the eye struggles to maintain a healthy tear film by, for example, not producing enough tears or when the tear film evaporates too quickly. This imbalance can lead to damage of the ocular surface and also discomfort for the patients. Dry eye disease can have multiple causes, but for example, wearing of contact lenses, which in our case, in the case of this study, the subjects were. A little bit about the diagnostic tools of dry eye disease. So current diagnostic tools for the dry eye disease remain a challenge due to a number of reasons, like the variability in symptoms and the lack of a unified diagnostic approach. Current methods can be invasive and uncomfortable, highlighting the need for an innovative and non-invasive diagnostic tool. Nowadays, the non-invasive breakup time, or also called Lipid, is the gold standard for minimizing the contact with the ocular surface. Therefore, we also would like to introduce a kind of a non-invasive breakup time test by introducing a dual visible and thermal imaging instrument that aims to address these challenges. So here you can see kind of a schematic overview of the experimental setup. So the device utilizes dual synchronized visible and thermal camera. First, the thermal camera is located just perpendicular on the optical axis of the ocular surface. And through this thermography, the relative temperature of the ocular surface is assessed, recognizable with the blue color in the slide. Conversely, the visible camera is positioned at a 90 degrees angle relatively to the ocular surface, facilitated by a dichromatic mirror. This camera records the ocular surface in where a disc grid pattern or placebo disc pattern is projected by the tear scope. A little bit more about this tear scope and how it is projected. So this tear scope has adjustable lights implemented in it, and together with the placebo disc is projected into the ocular surface. So this device is located as closely as possible to the ocular surface to have the placebo disc cover as much ocular surface as possible. The pattern will distort in time after the subject is not blinking and are captured and then also quantified by analyzing its deformations. So the main objective of these present studies is to use the dual visual imaging instruments to investigate the potential relationship between the ocular surface temperature and the deformations in the placebo discs. A little bit more about the measurement protocol. So we conducted this measurements on 23 young students enrolled in the computer science bachelor program at the University of Murcia, and these subjects were fitted with soft contact lenses manufactured by Alcon laboratories, intended to potentially enhance temperature variations, what I mentioned in the beginning. Also, simultaneously, video recordings are captured of a duration of 30 seconds, in where the subject is asked not to blink anymore, which is recorded with MATLAB. The frame rate of both cameras is 10 frames per second. So, a little bit more first about the visual image analysis protocol, which we can is identifiable with the red color throughout this presentation for more clarity. So the region of interest of the ocular surface, specifically in our case, is the limbus, is detected using a circular U transformation. Then after this detection, the region is cropped out of the original raw images. Next step is to determine edge detection. In this case, we used a canny edge detection algorithm to capture the grid-like pattern of the placebo disc. And the threshold of this algorithm is adjustable to achieve a well-defined edges. Transitioning to the thermal image analysis protocol. Multiple tracking points are selected to monitor this region of interest of the ocular surface throughout the 30-second measurements. A bounding box is constructed around these tracking points to crop out the region of interest. Within this region, the relative average temperature decrease expressed as a percentage over time is calculated, which is now shown here in this little animation. So moving forward to the results. Following the thermal analysis, the study recorded a maximum variation in ocular surface temperatures ranging from 5 to 41% across the measured subjects. These results, together with the observed distortions in the placebo disc pattern, recorded with the visual camera, corresponds to two general behaviors of the tear film, namely stable and unstable. To clarify these two general behaviors a bit in more detail, take a look at these two examples. In the stable case, on the left, a minimum visible distortion of the placebo disc is observed. This is paired as well with a uniform maximum temperature decrease of the same region of interest of only up to 5%. This suggests the presence of a well-maintained tear film. But on the other hand, the unstable behavior is categorized by significant visible distortions in the placebo disc, along with an abrupt local temperature decrease of at least 12%. These observations may indicate a rapid breakdown of the tear film. To clarify these two behaviors in more detail, we've included an example of the two variations in time. Firstly, the stable case. There's barely any deformations in the edge detection images. So this is paired as well with a small uniform relative temperature decrease of only up 5.2% in this example. But if we look at a more unstable case, on the other hand, we can see that there is a significant visible distortions observed in the placebo discs, together also with a more abrupt and larger relative temperature variations, with in this case a maximum of minus 14.8 18.4%. So locally, these variations mostly correspond across both channels. I hope it's a bit seeable, but here you can see the breaking of the temperature decreases, which is roughly corresponding with the breakage of the placebo disc edges. So, combining both imaging channels can offer a wider view of the assessment of tear film quality, as it integrates two types of information, the visible and the thermal. So this dual channel approach allows for a more local analysis of ocular surface behaviors, given the complementary yet distinct nature of the data obtained from both channels. However, there are preliminary exploratory findings of the subject wearing contact lenses, which may open doors for future research. Moving forward with more global findings. Here you can see the average relative temperature change in this graph. As you can see, there are a lot of variations in these results. But note that these results start at time is 5 seconds. So we avoid the sudden decay of the initially open of the eye, or maybe the change of pupil size. So to clarify a bit more of the previous mentioned two behaviors, two examples of the temperature changes of these behaviors are shown in red. The stable behavior is barely changing in time, while the unstable case shows a more significant temperature change. So taking a global approach of all these temperature changes findings, the average of these results are plotted in blue and with the arrow bars shown in the standard deviation. So moving back now to the visible camera, two change detection functions are used, which the first one is the entropy. As we can see that the edges fade away in time, the contrast between the pixels is diminishing. So this reduction in the variability leads also to a decrease in the number of distinct intensity levels present in the image, leading to a decrease in entropy. Again, a simple example of the stable and unstable behaviors, which are the same selected subjects as previously mentioned. And also, you can see again here the average with the standard deviation as the arrow bars. The second change detection function here chosen is the normalized count of the white pixels in the edge detection images. These findings also decrease in time due to the fading of the edges, and where the white pixels of the edges transition into black pixels. Same to show you the stable and unstable behavior of the same two subjects. And again, the average of all the data sets with the standard deviation. So, in the animation examples, we have seen that there is a local correlation between the two channels. But the question is now, is there also a global correlation? The answer is yes, although it's a weak correlation. We fitted a linear regression through these findings to determine this correlation. Here you can see the correlation between the entropy change, so the slope of the linear regression, and also the temperature change. While the correlation between the two channels may be low, integrating data from both channels could enhance diagnostic accuracy by providing complementary insights into different aspects of the tear film. The combination of these two channels may offer a more comprehensive understanding, leading to improved diagnostics, but further research is required to optimize this integration of the two channels, which I'm currently working on in my PhD program. I meant to say the research is not closed yet. Similarly, also there's a change in white pixel count. So, in conclusion, the simultaneously of the visible and the thermal images provide a unique perspective in the tear film measurements, allowing to compare the two methods. Firstly, the conventional visible images that allow a non-invasive measurement of the tear breakup time, nowadays the gold standard. Secondly, the thermal imaging that could allow us to obtain the thermal information of the ocular surface. So combining these two allows us to possible localization of tear film deterioration and can provide information on how the tear film is behaving. This correlation suggests that thermal instability can be an indicator of visible disruptions. The dual imaging approach represents a step forward in our ability to non-invasively monitor and understand the tear film dynamics. And that is all. Thank you for your attention.
Thank you very much. We have time for one or two questions.
Thank you very much for a very interesting presentation. My question is, maybe I missed something. For calculation of this relative percentage, did you use the Celsius temperature scale or absolute Kelvin scale?
I used just the gray scale images, or the gray images values, because I didn't measure it in temperature, so I'm only using the relative temperature to see from the start of the measurements and all the corresponding frames afterwards. Since it can be measured with FLIR software, but then the absolute temperature is not that precise, only the relative temperature is more precise. So that's...
But the relative temperature change depends on the chosen scale of temperature. If you calculate this using Kelvins, you get different values. If you use Celsius scale, you get different other values. Especially if you talk about entropy, which is some kind of a distribution of the energy, you should use the absolute scale of temperature because this is the measure of the energy. Okay, so I think that would be much more intuitive for me as a physicist, for example, to use the temperature scale that is somehow connected to the measure of energy. Okay, because then if you use other scales, you can get different results. Okay? But the phenomenon is quite interesting. Okay. Thank you very much.
Thank you.
I'd like to follow up with a somewhat similar question. I'm right here. Okay.
Sorry.
Yeah, I see your searching. So, did you, perhaps I missed it, did you make any attempt to make sure you were using the full dynamic range of your thermal detector? And if so, how did you do that?
Well, I did not use the full range since kind of the tear scope is a kind of in the way. So the shadow of the tear scope is making a black round in a thermal imaging. So in that case, I'm not using the full range of the thermal of the temperature.
No, within the possible range of measurements, did you make sure that you optimized your detection ability? In other words, maybe the temperature is only varying, you want to talk in degrees, 2 degrees.
Yes.
Right.
Mm-hmm.
Did you make sure that your detector was only detecting in the range of 1 to 2 degrees over the area of interest?
Yes.
So that you had a dynamic range. You did. And how did you do that?
Yeah, so I'm not really sure since I'm measuring it with MATLAB, it's not possible to have the absolute temperature only with this FLIR software, since the dual is not with that. So I did not correlate, or I did not change that. No, I have to look into it more. Yes.
Okay, thank you very much. I think we should continue later. You can catch her on the coffee break maybe, so we keep going. Okay? Of lipid deposition and absorption in silicone hydrogel contact lenses using spinning disc confocal microscopy. Thank you.
Very long topic, I think one of the longest. However, I hope that the presentation will be much faster, just to fill the 15 minutes. My name is Tomasz, it was mentioned. I am splitting my professional life into the academic, where I am doing my PhD study under the supervision of the Jacek Niewski at the University of Warsaw, and I am also working for the industry as a professional education and development manager at Alcom for Polish market. So today I'm going to talk about the visualization of lipid deposition and absorption in silicone hydrogel contact lens using spinning this confocal microscopy. And what is interesting most in this actually preliminary study, the part of my PhD study, is that we wanted to check if diffusion is good model to describe the very first time after lipid adhere or attached into the lens surface and then diffuse into the lens matrix. So let's jump into the world of contact lenses. And actually, I should skip this slide because all of you know what is the difference in thickness between contact lenses and the tear film. Here we have the OCT images of the cornea. This is the same patient without and with contact lenses, and you know it's quite hard to find there the thickness of the tear film. At the same time, the lens is quite thick. So this is something that interests me more, the interaction between contact lenses and the tear film. And actually, when we are looking at the tear films, there are the different models, of course, of the tear film, but one of them is presented here by the image, and you can see here that we have aqueous, which actually is most often described as the muceus aqueous fraction, and in the very top, the outside of the tear film, we have the lipid layer, which actually is described as the B layer, which composed from the phospholipids and also non-polar, but also some polar lipids. And from the clinical perspective, we know that the lenses can behave or perform totally different. When we are looking on these images, which actually from our other study, when we use the interferometry to look at the tear film in the different lens materials, you can see that actually you can look at the lipid part of the tear film, which behaves totally different in the same patients, the day by day, so the next day examining, and we can see that how this lipid layer looks like. And from time to time, from the, again, clinical perspective, we can see the patients with a lot of deposits on the contact lenses. And we also know that in terms of silicone hydrogel contact lenses, right now the most often fitted and most often used type, especially when it comes to reusable contact lenses, it can be quite problematic for the ECPs, for the eye care professionals. And just to add to that, this is the photo of the lens after wearing for several days, but this is the photo from microscope after 5 minutes of wear. And even after 5 minutes, you can see a lot of deposits on it. So that's why this is my area of interest. There is few years ago there was a lot of publication in this topic, and we know that silicone hydrogel lenses are more prone to lipid deposits compared to the hydrogel lenses. For example, for the cholesterol esters, and triglycerides. And we also know that different lens materials accumulate different amounts of lipids. However, my study is not to compare the materials itself, it's just to have better knowledge of the phenomena, how lipids attach to the lens and how they absorb into the lens matrix. At the last slide on this part, I just want to show you that this is the problem which is noticeable by the eye care practitioners. This is the study that we conduct in Poland, and the ECPs told us that they can see the lipids on the lens surfaces, and they know that there is some kind of connection between lipids and the problem with comfort and problem with vision. And going to my study, I will just briefly go throughout the methods. We use NBD cholesterol, so fluorescently tagged cholesterol, which allows us to visualize the agglomerates of the lipids on the lens surfaces, and also in the solution which was added on the lens. And we used 7 types of reusable lenses, just to avoid the situation that we choose one which have different properties than others. So what we've done differently than other research in this area is that we do not use surfactants to dissolve very well lipids into the solution. So we allow the lipid to make some kind of agglomeration. We did not control it, but actually we cannot control the lipids, and we don't know how they behave on the lens, on the eye surface perfectly. So after removal of the lens from the blister pack, we put it on the container with the PBS, and the PBS also have the Acto 847 with nanomolar concentration, which was very important for us to visualize the surface of the lens, which allows us to focus on the part of the lens which was very interesting for us. And after incubation in the 36 degrees of Celsius, the lens was removed, and we take it to the microscope. We put it on the measure glass, but in the bottom of it we put the 50 microliters of PBS. Then we put lens, again 50 milliliters of PBS, and thanks to the Acto, it was possible to focus on the lens surface. And in this point, we start the measurement for the 10 minutes. And at the very start of the experiment, we added onto the lens the solution with lipids, with lipid agglomerates. And here's the microscope that we use. So we use the size spinning this confocal fluorescent microscope, and it allows us actually to have bigger size of the sample, because without spinning this, it would be much harder to obtain the samples in high time frequency and also in the quite big space. However, this space is still 0.1 area of the lens, so it's very small. So again, it not allows us to compare lens to lens, because they can differ from the part to part. But what we've done this is the image after 10 minutes of the measuring. So the green lights represent the lipid agglomeration on the lens surfaces, and then we picked the biggest one, and we've done the precise scan in the X, Y, and Z direction. So we create the like 3D image, which allows us to then look at the cross section of the lipid agglomerates and the penetration of the fluorescent tagged lipid into the lens matrix. So a little about the results. The very first slide that I will show you next is the videos from the two samples of one materials, and you will see that this kind of different, because as I said, we cannot control the amount of the lipids. So here we have much more, and here we have less, but after 10 minutes in both lenses we see a deposits. So as I said, we choose the biggest deposits, and then we've done the visualization and some kind of calculation. Why we've done calculation? Because we want to know how these lipids behave in the time penetrating or absorbing into the lens matrix. So looking at the table, we have Z is the information where from, so maybe I will start with that. The peak is the place when we have the lens surface. This is the place where we have the biggest intensity of the fluorescently tagged cholesterol, and then we are looking where the density, the intensity of the fluorescent light is 0.2 from maximum, and this is the place what is called Z. So let's collect the depth inside of the lens. And we also checked how much time took from the lipid attachment to the lens surface to the end of this visualization, to taking these measurements. So with that, it was possible to make some kind of calculation to look how these lipids diffuse in the same amount of time. But it's actually only the calculation, because it's not show us the real data, real numbers, because the diffusion is not linear the whole time, because we know it depends from the concentration. So at the very start, the diffusion will be much faster than in the next minutes. So, and also it will depend from the lipid size. So we have to take into account not only the concentration, the time, but also the lipid size. And we can see that the same situation for the other contact lens materials. So for example, here we have Confocal A. So again, on the both samples you can see the lipid agglomerates attached to the lens surface, as well as we can see how they diffuse into the lens material. And I will show you briefly the other ones, because I think I hope you saw that not all of the lipids attach immediately into the lens surface. Some of them need to find the place to attach, or they will not attach at all. So here is for low traffic on air. Again, we have some kind of the difference, which is because of the different size of the lipids and different times from the attachment to finish the calculation. Another one, low traffic on B. It's not working. Oh, it should work right now. So not a lot lipids, but however you can see that some of them, this one is traveling a lot, but at some point it's detached. So, and again the results, difference, a big difference in terms of size, and also big difference in terms of the time. So even if this lipid attach as the first, the calculation showed that at some point the speed of diffusion is much lower than it was for the lens which was attached later. Silicone A. So this shows us also why we should use the bigger space of sample, because if we will choose only one without spinning this measurement, we will, for example, choose only this part of the lens and we will see nothing. So, and again the results from the lens samples. And Silicone A, I think here is one thing is quite interesting, because you can see at some point that you will see the big one here. So even the big lipids can attach to the lens surfaces, and however here is the representative of the most common morphology of the lipids that we found on the lenses, and this one, which attached much later, so the time for the diffusion was much shorter, have still totally different morphology. And we don't know what happens next. Maybe it will be attached more to the lens surfaces. And Silicone A, I think it's the last one, so not a lot of lenses is lipids in this sample. So we have also the numbers here, and more than that, we together with making little error, because one sample which was not presented here because we've done additional one, getting a little lower during the measurements. So we focus not on the lens surface, but little above it. But what we found there, that at some point we will see the big lipid, and at some point it attached to the lens surface. And then we were looking what is happening there. And some of the lipids will travel in a minute throughout it, upper from the lens surfaces, and actually nothing happened here. So he just go away. But other one attached to the lens, to the lipid, which is attached to the lens surface. So we can see the mechanism of the building up of the lipid deposits. So just to conclude, this method allows us to effectively observe the attachment of the lipid aggregates on the surface of the silicone hydrogel contact lenses, the different types of the contact lenses, but all of them were silicone hydrogel, but the different, built from the different materials. We saw that it's not possible in this configuration to have the same lipids size, and we have the difference in the times when the lipids attach to the lens surfaces, and they also differ because of the different sizes. They diffuse in the different, maybe not way, but in a different speed into the lens matrix. So the linear uptake is not very good model to take it, but when we take into account the lipid size, the time, I think that we can support that diffusion is a good model to look how lipids diffuse or are absorbed into the lens matrix. So some application for the future studies is, for example, this method allows us to make a very precise scan maps of the lenses with the deposit on it. So maybe it will be possible to use it to make some numerical simulation of the tear film flow onto the lens with and without deposits. So that's all from my side. I'm open to questions, maybe some feedback, some comments.
Anyone has any question? Okay, I was going to say I do, but let's go ahead, please. Please forgive me.
Hi. I wonder, why did you choose this particular imaging method? I know you went for fluorescence, but why this type?
Why this type? Why
Yeah.
confocal microscopy?
Yes.
Yes, for the resolution, for being in the microstructures to understand it better. Yeah? So I think that this kind of microscopy can give us very high resolution images in the small samples, of course.
What about two-photon fluorescence?
Actually, I didn't thought about it, to be honest.
Because I think it's got a better resolution, but I was
Okay.
just wondering.
Okay, thank you for your feedback.
You were.
Okay, we have another question.
Very interesting talk, thank you. I would like to ask if you have considered somehow standardizing that method against clinical part, because I'm a humble clinician, and what I'm interested in is like, could you like see if any behavior of that lipid influences more the patient, so to maybe in the future to develop a lens that will be less prone to those deposits.
Yeah, so actually this is the aim of my whole PhD study, to do something like that. So as I said, this is just the preliminary part of it, so more and more will come in this topic, I hope. Yes, this is something that I think that we are talking about the macro scale, to understanding the clinical situation. So to do that, we need to understand better the micro scale, and then we can jump into the world of the clinical part. Yes.
Okay, thank you. Okay, thank you very much. Let's
Thank
thank
you.
you, the speaker again.
Okay, guys, some of you may know me, I'm Izabela. I was the person on the other side of the computer that been answering your emails for the last couple of months, so you may know me from there. Those of you who were lucky enough to be at the VPO 2014 may know me as a student that was kidnapped by the magician. So, okay, so my study is about the dry eye disease, and already Spiridon and Pien made a good introduction about the dry eye disease, that it is a problem, it's a burden for the whole society economically, but Also for the patients, like people when they validate, they talk about how they feel with dry eye disease. They usually compare it through special questionnaires that are called the quality of life questionnaires to either the level of having severe tonsillitis or being constantly under dialysis. So this is the level of discomfort that some of the patients feel and some of my patients feel, because I'm a simple clinician, so I'm very humbled by your presentations earlier with the engineering and numbers, but into that practice I'll do my best to simplify the protocol, to make our life as clinicians easier, and to try to diagnose dry eye in a simple manner, because if you're not familiar with dry eye disease, I'll show you in the next few steps what we are going through usually to diagnose it. So, as already said, it is a huge burden, and everybody who knows, who works with dry eye and works with tear film, probably knows this definition by heart. This is the Dry Eye Workshop 2 definition of dry eye disease, which might soon is going to change, because in 2 months to come, there will be another dry eye report published after many, many years. Like a Bible of dry eye disease will be published in November, and that definition might gonna change a little. But what it's not changing up to now, it's that one simple word in that definition, which is the multifactorial part of dry eye disease. We started, actually, the first definition was pretty simple because it was taught as a just lack of water in the tear film, which is a little underestimated because it's a combination of many factors in the tear film that usually may not even be the less level of, let's say, lipid or water. Sometimes it's even too much of one of these factors. So they're combined. And this, because of this multifactorial nature, we have many protocols to follow. There is something that is called the vicious cycle of dry eye disease. It can start at any point from inflammation, evaporation, instability, and it can go, the patient can go through that vicious cycle. There are also protocols that say how to discriminate people with dry eye that is visible clinically under the slit lamp, under any specific machines that will follow the tear film. But sometimes there are patients who have every single clinical factor of dry eye, but they don't feel like having it. They've been having these problems for such a long while that the level of pain, the pain threshold, gets so high that there are no apparent signs when we ask them how they feel. Or totally opposite. Somebody has the clinical complaints about the dry eye, but doesn't have any clinical signs. And it's usually that those people go into a group of something like we call it the neuropathic pain, not dry per se, but some of these people need a solution. So ophthalmologists will take over, but to diagnose it, to make sure that it is the dry eye, specific type of dry eye, specific level of dry eye, everything requires a really complicated protocol. So I dedicated most of my studies to try to find a certain marker that would try to simplify the protocol and to be able to diagnose disease, not per se 0 to 1, but just like at the best at the incipient stage. Maybe it's too big of a dream to simplify the protocol and to have the diagnosis at the incipient stage, but most of my research is focused on that. And this is a simple study from one of these, me trying to simplify the protocol of dry eye disease. So one of the things that we tested with my group was that infrared thermography, like Pien already been talking about the infrared thermography, and it's pretty nice because during our research we were thinking it would be perfect to be able to follow temperature and tear film stability at the same time, which you did. So I will have a talk at the coffee break with you about that. Because we observed some certain correlations between those two, but but we didn't measure it simultaneously, so we'll have a lot to talk about that later. But the tearfilm thermography in dry eye disease diagnosis was published in some studies that there are differences between people without dry eye and with dry eye. However, there was no, until this moment, a study that would somehow put them in order in terms of severity. It was like 1-0, and some of these studies even have different results. Most of the studies said that the dry eye is colder. At first sight, for me, it wasn't that. Like at the beginning, I thought it was going to be warmer because it's inflammation, but it's definitely way colder in dry eye disease than it is in a healthy eye, in a control group. But there is a clinical difference, but it follows a route that is not only based on the Newtonian law of cooling. Like we know that when there is a warm body, there is a surrounding, the bigger the difference between the body and the surrounding, the cooler should go faster, the rate of cooling should be bigger. But in dry eye disease, in tearfilm, it's a connection between those two. So if the body is warm, it's inflamed, it gives the temperature quite quickly, but also we have the tear film that covers the ocular surface, and when it evaporates, it breaks. It exposes the cornea, which is a vascular, which is a bit cooler than the surface that is vascular. And it is a pretty quick and non-invasive technique, so it already demonstrated a really good repeatability, and in our study it also was visible that it has way better repeatability than, for example, non-invasive breakup time, which is actually a pretty positive observation of it. So the aim was to evaluate the utility of non-contact infrared thermography on diagnosing dry eye disease severity. And there will be a few observations on that. The methods that we use a thermal camera, a FLIR T640. I'm not that big of an engineer, like some people helped me with taking care of that camera, but as far as I'm concerned, this model doesn't exist anymore. It has a different name, but it was specifically chosen for the design to work on the ocular surface because this has very good thermal sensitivity in that 30 degrees Celsius area that we expect to get from the ocular surface. And it was placed around 25 centimeters from each patient perpendicularly, and we assessed a 10-second period without blinking, so it was suppressed blinking conditions like it is in breakup time, and we followed the temperature right there. And from the 10 seconds, we chose 1 hertz, so once per second, every frame that we fitted with a protocol that would accommodate all the, respect the palpebral fissure of each person, so the natural geometry of the ocular surface. And we measured the temperature, the average temperature, standard deviation of the temperature, minimum and maximum in each of these 13 areas. I actually showing 13, it was 16, but those are the small dots you can see here. 13 small 3 millimeter diameter areas on each of these points. And we had to also put our subjects into groups, and this is when it started to get a little bit tricky, because I already told you that the protocols are pretty heavy to diagnose dry eye itself, and what's more, to diagnose each level of dry eye disease. And we used the aforementioned dry eye workshop 2 report to diagnose it. It's usually based on 3 markers, which are called the markers of homeostasis, which is the NICUT, or non-invasive teeth and breakup time, tear osmolarity, and the the staining of the ocular surface with fluorescein, plus the symptoms. So this is the basics that we can do clinically to diagnose dry eye, like to compare it from the control group. But to further divide people into different severities, we took each of these markers, knew the threshold that it has between healthy and unhealthy patients, the dry eye ones, and put those markers that we call markers of severity in order. So the more of these markers the patient had, the more severe the disease was. And it divided our subjects into mild, moderate, and severe version of the disease. The severe subjects were usually the ones with something which is called the Sjogren syndrome, which causes the lack of aqueous tears in the tear film. And the table may look a little bit chaotic, but this is for you to show you how big of a protocol it is to go through just to diagnose dry eye disease. All of these tests that are mentioned here are required by the standards that we have now. So it's a pretty huge protocol that we need to follow, and it would make our life simple if we had like a simple biomarker that would accommodate these. The results, these are just the examples how it looked like. So the temperature changed through time, and the minimum and maximum temperatures in those particular area weren't that much of an interest. I mean, like, we could assess based on them what's the minimum and maximum temperature on the human eye, but the averages and standard deviations of these were following the time. They were behaving temporal changes, and we saw that the average temperature, of course, drops in time, but what is even more important, the standard deviation in those small areas was expanding in time as well. And this was actually was seen as a better version of what is happening with the tear film. So not the average ocular surface, but also in some cases, but the standard deviations of those temperature when the tear film breaks, it increases the standard deviation of the temperature. And those together, those two factors, were found, like when we are comparing each of these severity groups, were shown to discriminate between those groups that we assessed in the study. So controlled, mild, moderate, and severe dry eye cases. Which is a good thing, because usually when we diagnose dry eye disease, if it's severe, we already know it. We see it on the ocular surface. But the moderate, mild cases are pretty tricky. So this method showed that we can use the thermal camera to assess it, to assess the differences between controlled and mild cases. But it worked just for the particular areas of the ocular surface. So together with the ROTA quiz here and the group of biomedical engineers, we thought, why just those areas? Those areas are specific because they show interactions not only between the eyelid area, tear meniscus, but also limbus and cornea. So they take many factors into account, how the tear breaks, and how the eyelid surface warms up. But then some of you may ask, why not these other, the blue ones that are on the nasal side of the ocular surface? Why just these two? So the cornea were already well defined, the coolest area, but why not these? The particular and the nasal side and the tarsal side of the ocular surface. And it's because those areas are close to something which is called the lacrimal caruncle, caruncula lacrimalis, which is vasculated and pretty warm. It's on the same level as the human body, but also when the eye gets inflamed, we found correlations between the level of tearosmolarity and the ocular redness that was correlating heavily with the temperature of that part. So So if you, let's say, diagnose inflammation before cataract surgery, as one of the researchers already did so, trying to investigate the inflammation before the cataract surgery based on the thermography, this is the spot to look for. If you look to diagnose dry eye disease, you should go to the areas that are near the eyelid margin. And why not Nigbut? I really like Nigbut as a clinician to use it at the tip and breakup time, but if you ever measured tip and breakup time, you know that you have to measure it 2-3 times, sometimes even more, to have a specific diagnosis. It depends, of course, what devices you're using. Some of these are pretty good in assessing them, but the coefficient of variation and the repeatability of these methods is low. And here, when we measured the ocular thermography three times in a row, I haven't mentioned that, but we did, the temporal changes that we measured and the results that we got were very, very similar. The coefficient of variation in the whole study was around 2% for these measurements. So for me, as a simple clinician, it means less repetitions, less chair time. So it simplifies the protocol. And of course, there are several limitations. The main one is the multifactorial nature of the dry eye disease, which may sometimes cause overlap between two groups of subjects. The mild cases and control group may still be overlapping a bit. But even though the ocular thermography showed that it showed significant differences between groups, even though that the groups were pretty close to each other in terms of severity, it shows that it works and it could be used maybe instead or maybe as a support to tear film breakup in the future for diagnosis. And thank you for listening to me and for your cooperation before through emails. I appreciate it.
And now we have time for questions.
Do you have an idea what is the reason of the difference in the temperature of the cornea and conjunctiva on the 14th slide?
I have my thoughts about it. Mainly it's because of the vasculature. So the conjunctiva, even in a very healthy patient, has a lot of blood vessels, so it warms up. And it's more like when we were talking about the nasal part, so it's more inflamed with when there is an inflammation, ocular redness, it gets warmer. So with the group, we thought it definitely needs to have something connected with the vascularization of the area. Cornea should be, at least, because in some cases is, but usually it's avascular. So there are no blood vessels that will get the warmed up blood to that area. So this is my thought on it. That it's the coolest part.
And you cannot visualize vessels. It is not this resolution.
With thermal camera, not like, but with visible one, as we heard earlier, you can do this pretty with Claritas protocol. You can do this pretty well. So.
Thank you.
I have one question. So you said you like or much Nibud. Do you really feel that?
I have to kind of.
You have to use it every day. Do you really feel that that thermography could substitute Nibud in the future? Because my thinking, it's like maybe Nibud it's more variable between different measures, but I feel like the thermography depends much more on the external factors. Like it's very affected by the temperature, humidity, and even I think the body temperature. Mm-hmm. So what do we get? Like a variable technique or
this is also what I thought, because as a clinician I don't like to use a sophisticated equipment for such a simple diagnosis. But then if we focus on the areas that I pinpointed out and maybe simplify in the future, because there are tons of thermal cameras. The one we use, as far as I'm concerned, is pretty sophisticated, but the plan is to test it on some simpler devices and see if it works. Because with Nickwood, you know it exactly well, that it also maybe not even so much depends on the external factor, but sometimes it's tricky to make an average out of even 3 measurements. So, and plus, to measure Nickwood, you have to measure only also the osmolarity and some other parts that are included in the protocol. With the thermal camera, you may get some things out of that protocol. I don't say that you don't stain the epithelium, but maybe perhaps skip the osmolarity, or there were some correlations that I shouldn't show with the way the meibomian glands look. So it will save us some chair time maybe in the future. But of course it will be need to investigate it if we can use a simpler device, because this camera is pretty heavy equipment.
Okay, thank you. Any other person? Okay, so with this, we finish the last session of the conference. Well, the last, yeah. And now, do we have a coffee break? Yeah. We have a coffee break, and the organizer is close.